Alright, there's one thing that I forgot to mention about hybridization. Let's take the example of an 2sp2 hybridized orbital. Sorry, excuse me. What I forgot to mention is that you have to take in consideration the three-dimensional shape, or the orientation of these orbitals. What I mean by that is that, as you should know, p orbitals take up different axes. Uh, you can have one running around the x-axis, the y-axis, and then the three-dimensional z-axis, the one that goes up and down out of the plane. So what's important to realize in an sp2 hybridization is that you are taking two p's, two p orbitals, and mixing it with one s orbital. If you add 2 and 1, you are making 3 orbitals. You are making 3 equal energy orbitals right here. But what's important to not forget is that you have this one unhybridized orbital. You conserve this 1p orbital, and that is shown in this picture right here. We have our two, sorry, let me write that in its color. You have your two P SP2s in green. Now notice how I use the x and y p orbitals. That means that the hybridized orbitals lie along the plane. That means anything that bonds to these hybridized orbitals must lie in the plane. This is very important. This accounts to why double bonds, or molecules that have double bonds, are flat and you cannot rotate them. It's because their bonds, their direct sigma bonds, lie within the plane. Now, what this sigma, or not sigma, what this p orbital does, this p orbital that's pointing up and down from the plane, it's sticking out in like three-dimensional space, is that it interacts with other molecules, creating a pi bond. And that's important because pi bonds are essential to making double and triple bonds, and I'll explain that later.